thanks to the organizers for the invitation to talk about my work here. So I work in an area of topology that's called surgery theory. So I will divide my talk into two parts. First will serve as a motivation for surgery theory. And since I'm a co-author of a monograph on this topic that was published last year, it will also be describing that work. And in the second half, I will give application of this theory or of the tools of surgery theory to a concrete classification problem of manifolds that was presented in a PhD thesis of my student Ajay Raj, who defended in this August. So let me start with the main object of study in this area, which are topological and smooth manifold. So a topological manifold, does this work? Okay, so a topological manifold is a space that locally looks like a Euclidean space. So that means that you have so it's perhaps something like this torus, and that locally looks like a Euclidean space, since you can for each point you can find a neighborhood that is can be identified with some open set of a Euclidean space. So such spaces do occur in mathematics a lot. So here are some easy examples. So for example, a sphere, a product of spheres, surfaces, or Lie groups, or there are many examples from algebraic and differential geometry. So this is very nice, but it turns out that if you want to do analysis, for example, because you want to study the dynamical systems on such things, this is not enough. So it's not enough to have a space that's locally Euclidean. Why not? Well, because that space may be locally Euclidean in two different ways. So for example, you could have two different identifications, phi alpha and phi beta here, and they may overlap. And now it could happen that the transition function, so the phi alpha inverse followed by phi beta, might not be smooth, and so that would be bad. So to avoid this, one considers what is called the smooth structure on a manifold. And what is that? That's a collection of such identifications. So these are called charts of parts of your manifold with Euclidean space. So it's a collection of such things where we require that these transition functions are smooth. Okay, so that these transition functions are smooth. And if you have such a collection on a topological manifold, then that collection is called a smooth structure. And if you have it, then you can do analysis in a meaningful way, because partial derivatives, for example, make sense in this way. So so this is something that you want. And it turns out that luckily all these nice examples that we know do have such a smooth structure. So you do have a structure of a smooth manifold on these guys. However, it's not clear whether you have such a structure on any topological manifold, and also it's not clear if you have one whether you may have some other non-equivalent. Okay, so and that's part of the question that we address. We need some terminology. So we say that two manifolds are homeomorphic if they are topologically equivalent. So that means that you have a smooth map. That you have a continuous map whose inverse is also continuous. So it's continuous bijective map whose inverse is also continuous. And we say that a map between smooth manifold is a diffeomorphism if you have a homeomorphism that's compatible with these smooth structures. So we do have these concepts, and we do have some interesting questions, namely these classification questions. However, in this area, you have even more general classification questions. So the most general one is that, suppose that you have two manifolds, topological or smooth, does there exist a homeomorphism or a diffeomorphism between them at all? So, and for this question, people in algebraic topology developed many tools, and so I want to recall some of them. So the two most known are called homotopy groups and homology groups. And the first one of the homotopy groups has a special name, namely it's called the fundamental group. And so I will not give precise definitions, but just some ideas. It's defined using loops in a space X. So maps from closed interval 0, 1 to X, which start and end at some point. So that's something called a loop. And you can organize such loops into a group, and it's called a fundamental group. And this is a nice invariant because it somehow measures holes, one-dimensional holes in a space. So so that's basic philosophy. This has a higher dimensional analog where you don't map, interval, but you map a k-dimensional cube, and the boundary of that cube goes to a base point. This somehow measures k-dimensional holes. So that's something that we have. However, these groups tend to be not so easy to calculate. The fundamental group is relatively easy to calculate, but these higher homotopy groups may be harder to calculate. So there exists something else called the homology groups that I will not describe how they are defined, but it turns out they measure k-dimensional holes in a slightly different way. So the definition here is could be hard, but what's important is actually the properties. And so the key property of these invariants is their functoriality. So it says that not only for each space you do have these homotopy or homology groups, but also for a map of spaces, you do have these maps induce homomorphisms of groups, and they have the property that if you have a homeomorphism of spaces, then it induces isomorphism of groups. So if you have this property, then you can distinguish spaces, namely you can sort of prove that spaces are not homeomorphic, because what do? You could calculate these invariants, and if these invariants turn out to be not isomorphic, then you know that there could not have been a map that would be a homeomorphism. Okay? So this is a basic principle of algebraic topology. You have a topological problem and you transport it into algebra where you solve it, and then you have some solution in topology. So this was done successfully. So here, this picture sort of is an intuition about the fundamental group. So for example, this loop here measures the hole that's inside that space, little x. So that's a little bit of a picture for the fundamental group. And the picture here depicts the use of the homology group to distinguish surfaces. So this is a surface with 3 holes. So it's called surface of genus G. And one can calculate that if you have such a surface with G holes, then the first homology group is Z to power 2G. And so if G is different than G prime, then Z2G is not isomorphic to Z2G prime. And that's the way how we prove that if you have surfaces with different number of holes, you cannot, they cannot be homeomorphic. So this is basic algebraic topology. And so algebraic topology is very good in distinguishing spaces. So telling you that the 2 spaces cannot be homeomorphic. But you can ask yourself, can it also give positive results? For example, you can be able to calculate these invariants. And if they are isomorphic for the spaces, can you then conclude that the spaces are homeomorphic? And the answer is in general no. So that's a little bit bad, but you still ask yourself, can you still get some positive results? And you can get some positive results if you relax your demands a little bit. So you don't ask for homeomorphism, but you ask for something else. It's called a homotopy equivalence. That's something weaker. So a homotopy equivalence, it's defined to be a map such that it has an inverse up to homotopy. So it says here that you have a map in the other direction such that these 2 compositions are not equal to identity, but they are homotopic. Homotopic means you can continuously deform into identity. So this is something that's weaker than homeomorphism. Okay, but it's something, okay? And what's great about algebraic topology is that in this equivalence you have both implications. So a map is a homotopy equivalence if and only if it induces an isomorphism on homotopy groups. So if you have a homotopy equivalence, you have isomorphic homotopy groups, but also conversely, suppose that you have isomorphic homotopy groups, you can conclude that you have homotopy equivalence. So, you have lowered your demands and you can get this result. So now we have 3 equivalences between spaces: homotopy equivalence, homeomorphism, and diffeomorphism. And diffeomorphism implies homeomorphism, and homeomorphism implies homotopy equivalence. But the question is, what about the other implications? And the answer is no in both cases. So homotopy equivalence does not imply homeomorphism, and homeomorphism does not imply diffeomorphism. There are very famous examples. Milnor proved discovered exotic spheres, which show that homeomorphism does not imply diffeomorphism. In other words, he found 7-dimensional manifolds which are homeomorphic to the standard sphere but are not the diffeomorphic. Okay, that's a very famous example in 1956. And there are other examples that also show that homotopy equivalence does not imply homeomorphism. For example, if you have a product of spheres and at least one of them is has dimension 4k, meaning divisible by 4, then you do have a counterexample in this thing. So yeah, so you have so you have this situation, and so what surgery theory does, it actually does measure difference between the homotopy equivalence homeomorphism and homotopy equivalence and diffeomorphism. And so in order to sort of say it, I need a little bit of formalism, and the formalism is what's called the structure set in the sense of surgery theory, which has two versions, topological and smooth. And so this is a set in which all manifolds homotopy equivalent to X are organized, and together with the homotopy equivalences to X, and we say that two such homotopy equivalences are equivalent if there exists a homeomorphism from M0 to M1, which is compatible with these homotopy equivalences. That's the topological version. And in the smooth version, you have smooth manifolds, and you ask that here you have a diffeomorphism. So if you have this, if you have X and you have and you know this set, then you know how classification of manifolds that are homotopy equivalent but not necessarily homotopy equivalent to X looks like, up to either homeomorphism or diffeomorphism. So this is our goal, that's what we want. So this is the goal of surgery theory, to calculate the structure set. And Milnor's example shows that the smooth structure set of 7 spheres is not just consists of 1 point, and the other example shows that this one does not consist of 1 point. So these could be interesting sets. And so this is what surgery theory does. So yeah, so I'm a co-author of this book together with Wolfgang Gluck. It's called Surgery Theory, and we also have contributions by Dermot Crowley from Australia. It's 970 pages, so I'm not going to talk much about it in this 20 minutes talk. But at least I want to give you a little bit of flavor, some philosophy, what's behind this. And so I'm going to quote the theorem. That's the kind of main theorem of this theory here. It's a longish one, but I will try to sort of make sense of it. So it's due to Browder-Novikov-Sullivan wall, and it's called the surgery exact sequence. So notice that there is some sequence of some things. So it has two versions. It's both topological and smooth. So let's say in the topological version, it's an exact sequence of abelian groups. And here you have this thing that you want to understand. That's that structure set. Now, what is exact sequence? Exact sequence is some algebraic tool that's defined in terms of images and kernels of maps. It's not really important how it is defined, but the point is that if you have some group that you are interested in, for example, this topological structure set, and you know everything else in that sequence, then you know that group, right? So that's basically the idea that one calculates this structure set because one makes, it sits in this exact sequence, and you hope that you can understand the other things. And the good thing is that in good circumstances you can understand these other things. So these terms that are called N, top here, they're called normal invariants, and there are some generalized version of those homology groups that I've talked about before. So actually people in algebraic topology can say quite a lot about this. Then there are some other groups, these are called L groups, and they are difficult in general. Somehow they are described in terms of quadratic forms over a group ring Z pi, which is something that can be very, very hard. But, what is pi? Pi here is actually the fundamental group of your X. So in a good situation where this is trivial, this ring here is just Z, and so these groups are then defined in terms of quadratic forms over Z, which is also not so easy, but can be somehow understood. So actually in that case, these L groups have just this very simple form. So the general idea is that this object that we try to understand is understood in terms of some traditional algebraic topology plus some quadratic forms and some maps. So there is a nice picture that sort of describes the philosophy that's behind this, and where also the name surgery comes from. So the idea is that if one has two elements in the structure set, one first tries to put some manifold of one dimension higher between them. So that's called a cobordism. That could be some manifold with some holes like this. And then one tries to get rid of these holes, and in order to obtain something that looks like a cylinder, because then you know that the two manifolds are, the two ends are the same. And the surgery comes when you try to get rid of these holes. And the process of surgery is described here. For example, you have a torus, you don't like this hole here. So what do? You thicken it a little bit, you cut it out, you have something with a boundary, and then you glue two discs, and you get a sphere that does not have these two one-dimensional holes. So that's roughly the idea, philosophy that's behind that exact sequence that was on the previous slide. And if you are interested in more of this, then I can tell you about it, because I also have a poster. So let's now not talk much more about this, but let's talk about the results. So this theory has been applied successfully. The first row is the most famous example, where you have a smooth structure set of a sphere. And notice that the first non-trivial case is in dimension 7, and there are 28. And so this group is actually Z mod 28. So that means that these Milnor's example of exotic 7-dimensional spheres, they are examples here, and it turns out that there is one standard sphere and 27 some exotic spheres. So that's kind of something that's quite interesting. Calculations have been made for other manifolds, mostly in the topological category, for example, for the list that's here, that stuff that comes from algebraic geometry, and so on. And there have been made many calculations, but there are also some also by me, but there are also some open problems, and I can again talk about it sort of later. But in the last 5 minutes, I hope I have 5 minutes. Oh, 3, okay. I would like to talk about the how this theory was applied by my PhD student Ajay Raj. So what did he do? He studied this example. If X are sphere bundles over spheres. Why was he doing that, or why we were interested? We were interested mainly because in the smooth category, there exists example of spheres. And this was also done for products of spheres, but not much more. And the sphere bundles over spheres will be a logical next example. So let me quickly say what are fiber bundles, and then I will say the result. So fiber bundles are interesting things. These are kind of generalized products. So these are a map is called a fiber bundle if it locally looks like a projection from a product onto one coordinate. So maybe rather than doing this, I will show you a picture. So both the famous Klein-Buttel and the torus are fiber bundles over S1, because there are these natural projections from the Klein-Buttel to S1 and from the torus to S1, which locally look like a projection. Here you have a product of U with S1, and here you also have a product of U with S1. So locally it's a projection, it's a product, but globally, in this case it is a product, but in the case of Klein-Buttel, that's not a product. So these are some sort of funny, interesting spaces. And generalizing this, you can consider these are both S1 bundles over S1. You can consider SP bundles over SQ. Good thing about this is that such things can be constructed from maps from spheres to orthogonal groups. And there is some construction which I don't have time for, but again I can explain when you come to the poster. So the upshot is that that if you are interested in so what was this? So if you are interested in SP bundles over SQ, they can be constructed out of some homotopy theory. And so here's Ajay's thesis. So the goal was to calculate both the topological and the smooth structure set if X is such a sphere bundle over a sphere. And he was concentrated on cases where he had 4K minus 1 sphere bundles over 4K. In this case, it's known that such things are in bijection with the group Z plus Z. So we have infinite number of such things. Namely, for any two integers m and n, you get such a bundle. And so you can pick each of these individually, and you can look at those structure sets, so all manifolds homotopic one to it, and classify them up to homeomorphism or diffeomorphism. And so what are the results? So Ajay calculated that the topological structure set is Z mod 2n. So it's a finite cyclic group that looks like this. So that was a relatively straightforward thing using the surgery theory, but more interesting was that he was actually interested also in the smooth structure set, which was not completely determined, but it was determined what's the image of the map from the smooth structure set to the topological, and it is this subgroup of this finite cyclic group. So there is some specific number that can be calculated, and but it turns out this is always a proper subgroup of Z mod 2n. So that tells you that for any such manifold here, that's homotopy, for any such manifold Mnk, there exists manifold homotopy equivalent to it, which does not have any smooth structure, for example. So that's kind of interesting. So there are lots of, so upshot of all of this is that there are lots of kind of interesting examples of non-trivial manifolds, and in his work he also describes the representatives, let's say, of this subgroup. So that's kind of very interesting. So I think my time is over, but I would still like to sort of okay, so good. So I have maybe 1 or 2 more minutes. So okay, so surgery theory is in general about these funny spaces. Okay, so you have some manifolds that are either don't have a smooth structure, or they're homeomorphic to something standard but not diffeomorphic. So it's about sort of finding these strange spaces, and it's kind of curious. You get some of these generalized Klein buttles. It's very pretty. However, I'm not really aware of many applications of this to sort of real world. Although there exist some papers in physics that do mention exotic spheres, for example, but I'm not really sure that there are really real-world applications of surgery theory specifically. However, I'm 100% sure, I mean, there exists plenty of applications of standard algebraic topology, namely these homotopy groups and homology groups, to all areas of science. So, for example, there are many applications to dynamical systems. That's, by the way, where topology originated. There are applications to differential algebraic geometry. There are applications to condensed matter physics, field theories in physics, and maybe what I want to stress more is that since this is a conference for all of our faculty, we also have computer science, and so there are actually also applications to computer science. There does exist something called topological data analysis and even topological deep learning. So there really do exist methods where one tries to apply these topological methods to study data. For example, to solve classification problems of data. And I'm happy to talk about it. I also have a master's student who works on this area. So if you are interested either in the details of those funny spaces from surgery or these applications to the real world, you can talk to me in the poster session afterwards. So, well, yeah, and thank you. So, yeah.